Right, today's lecture is damped harmonic oscillators. And so what we're doing is taking the system that we had yesterday, which was a spring connected to a mass that's sitting on a frictionless surface. That mass is free to oscillate backwards and forwards. And now what we're putting in is an additional mechanism that enables the system to be mechanically damped. In other words, it can lose energy as a function of time. One way to imagine this, if you think back to your first year electromagnetism lecturers, it would be to have a rod connected to a metal plate, copper plate in a magnetic field, and there you rely on the magnetic field pointing through the plate. As the plate moves in, it generates eddy currents, and those eddy currents dissipate energy, and so you get a slowing. And so you've probably seen this demonstration in first year. You basically take a pendulum that's got a metal disc on it, you have a magnet down here, and when you drop that pendulum into the magnet, it stops pretty much dead as soon as the plate gets inside the magnet due to the eddy current effects. So we're going to look at this today less from a electromagnetic perspective and more from a mathematical perspective of how does this affect the dynamics. And so what we need to do here is add in an additional force into our system, and this is now a damping force that essentially resists the motion. It resists the motion in such a way that it's dependent on the velocity of the system. Okay, so you could imagine this to be an aerodynamic drag force, you could imagine it to be some eddy current force, it could be anything you like. And what we're going to do is take the simplest approximation to this thing. We're basically going to treat it linearly in velocity and have a sort of constant of proportionality that we call c. So what we'll have here is a minus cx dot. Okay. I did the Lagrangian approach yesterday. It was a little bit more work. For these really simple problems, we're better taking a Newtonian approach. So I'm just going to do that straight up today. Okay. So if we were taking a Newtonian approach to this, we would have our total force is going to be two components here. There's a Hooke's law force and there's a damping force. And those are going to be equal to mass times acceleration via Newton's second law. Okay, so what we would have here is mx dot dot is equal to minus kx minus cx dot. And of course we can take the two terms from the right over to the left hand side. So this would be mx double dot plus, let's carry the terms in order. So cx dot plus kx equals 0. And this is what you would normally call a simple damped oscillator equation of motion. Okay, a really common thing in here. And of course, if you're dealing with more complicated models of a realistic system, you might have slightly more complicated terms in here, but this is about the simplest case you can build for a damped oscillator system. Okay, so we're pretty much at the same place where we were yesterday. We have a second order linear differential equation that we need to solve, and so we can take pretty much the same approach of guess a trial solution, insert it, see if it works, come up with a better solution and work your way from there. And we're going to do exactly that today. So we'll start with the same trial solution today. Our trial will just be x of t is equal to EQT. And we'll just run this through because what we need to do, as we saw yesterday, is generate an equation that we need to set to 0 and solve that thing and start using that to understand the system. Okay, so we would have here m d squared on dt squared of EQT plus c d on dt of EQT plus KEQT equals 0. And of course we can do these derivatives. I won't do them step by step. We'll just work. We saw enough of them yesterday. So the first one up the front is going to give us a q squared. And as you know from yesterday, we can pull the exponential term out the end. So let's do that straight up. So we're going to have mq squared plus Our second term is going to give us a CQ. Our third term is going to give us k, EQT equals 0. Okay. And of course, same as yesterday, we can't really take this exponential here and make it equal to 0 because that corresponds to either time equals plus infinity or minus infinity depending on the sign of q. And so the correct thing here is to basically take this and make it equal to 0. And this is what we were calling yesterday our auxiliary or subsidiary equation. Okay. All right. So now we've got this thing. And what you'll realize is that unlike yesterday where it was linear, well, it wasn't linear actually. Yesterday it was a square equation, but it was simpler than the one that we have now. Okay, so yesterday's quadratic was a little easier to solve than today's quadratic. And so here what we need to solve is mq squared plus cq plus k equals 0. And the solution to that looks a little bit like this. Q equals minus c plus or minus square root of c squared minus 4mk on 2m. Okay. And as you know, for binomial problems or quadratic problems that you'll have done in high school and first year university maths, the thing that's really important in quadratic problems is the term inside the square root called discriminant, because it kind of determines the nature of the solutions that you're going to get out of this. Okay, there's c squared minus 4mk, and so what happens in here is we get 3 different cases, and we can look through them now. There's case 1, case 2, and case 3. Let's write them up. So the first one is that c squared minus 4mk is greater than 0. And this is the case that we call overdamped. And the important aspect of our overdamped solutions is that we end up with q values here that are real. Okay, and so if you think about back up here, this exponential now, if we have a real in for q, it is going to be a decaying tail in that solution. The other case that we have in here is c squared minus 4mk is less than 0. And it's a situation that we call underdamped. And here the q's have imaginary components. Let's for the moment just say that they're complex. And as you know, in that particular situation, if you have an imaginary in your q, you basically would get a wave. And if you have some real component, you get a tail. And so you can imagine here you might get a wave that tails off. And that's exactly what we'll see later on, coming from the fact that q is complex. And then there's a limiting case in between, c squared minus 4mk equals 0. And this is a case that we call critically damped. And so here the q's are still real. They're right at the point where they're transitioning from being real to being complex, and we're on the boundary between 2 different types of solution. Okay. So the way I'm going to do this lecture today, I'm going to deal with the overdamped and critically damped cases in the first half, just to keep the recordings compact. Cluster those together. The underdamped case takes a little bit longer to do, so it will be in the second half if you're looking for it. And I'll do possibly a little bit of a demonstration off the end of that, which will also be at the end of that second video. Okay. All right, so let's rip into our overdamped case then. So I want to come back one. We have two different real solutions of Q, and we need to basically work through those two different solutions. So those two solutions are, we can call them Q1, and it will be minus C on 2m. So all we're doing is just splitting up this, splitting up the quotient above, plus open brackets C squared on 4m squared minus K on m. And Q2 is just exactly the same thing with a minus sign in between the two solutions, right? Like so, okay? Now, one thing that we know here straight up is that Q1 and Q2 are both negative. And the reason we know this is we know that M and K are strictly positive, right? They must be positive numbers. We defined them as such. There's no meaning for a negative mass, and there's no meaning for a negative spring constant. Because of that, we can write the following relation. The square root of C squared minus 4mk has to be less than the square root of C squared. And the square root of C squared has to be, well, less than or equal to C, okay? And the reason why I have the less than or equal to here is because what I'm really saying here is, I guess, equality in this case, right? But if I consider this case, it's less than, okay? That's what I mean by that notation just there. And same if you see it in a book, that's essentially what they're trying to imply. And that basically comes about because if I take C squared, C is also a positive number. Well, even if it's a negative number, when you take the square, it's a positive number. If you subtract 4mk, m's positive, k's positive, so you must be taking a positive number, subtracting a positive number. That will give you something that's, in this case, strictly real, because up above we're dealing specifically with the overdamped system where we know that that term is greater than 0. And then that's got to be smaller than square root of C squared, okay, which is then equal to C, right? And so what we can say in here is if this term over here on the right is smaller than this, this term over here on the left is smaller than this term over here on the right, then minus C plus square root of C squared minus 4mk must be less than 0, okay? So what we're doing is we're taking a bigger number, making it negative, and then adding a smaller number to it, and that is always going to be negative. And then, of course, if we change this sign in here to be negative, then we're taking a negative number and we're subtracting something from it, so that's going to be negative 2, okay? So we know that both Q1 and Q2 must be negative numbers, okay? Now, the way we normally handle this problem is to assign two positive numbers to make things a little clearer, okay? And it'll seem a little weird at first, oh, we're going to assign some more numbers to make things more clear, but bear with it, you'll see it come a little further down the road. So we're going to have gamma 1 is minus Q1, and we're going to have gamma 2 is minus Q2, okay? And the main reason why we're not just arbitrarily changing the sign here is we want to just keep track of what's going on and not break things when we get to other solutions, okay? All right. So we know two things here, and we can pull it from our experience yesterday, right? One is that we know there's two solutions, so we have to have two terms in our beta trial solution, and we have to carry prefactors out the front, right? So our beta trial now is going to be x of t is a1 e minus gamma 1t plus A2e minus gamma 2t. And I could always have called these things up here Q2 and Q1, but you can see I've switched over to gamma so I can get the minus sign in there. And I want the minus sign in there knowing that gamma 1 and gamma 2 are positive numbers now, so that it's really clear that this is going to be an exponential tail off. Okay. So basically what we've got here is sum of two exponential decays. We're not going to take this any further. You could go through now and use boundary conditions to work out what A1 and A2 and so forth are. Often it depends on the problem you're solving and how to do it, and I don't want to get tangled up in that maths. It will take us half the day. But what I want to do is just quickly graph what this thing sort of looks like. You don't end up getting just a clean exponential tail in this overdamped situation. What you get is an exponential that depends a little bit on your initial conditions, and this is basically why we're not solving for A1 and A2, because it depends for a specific problem on what your initial conditions are. You know, where you are in the phase of the wave when your damping kicks in, what the various terms look like, and so forth. So you can end up in a situation where either you get what looks like a clean exponential decay, or what looks like a very quick continuation into an oscillation and a die-off. And if you think back to sort of this eddy current damped pendulum, you might imagine this being a case where it swings just through and comes back, right? And one thing to bear in mind here is that it looks, if you just plot it linearly of x versus t, it can look like it is a clean exponential, but if you actually look at the, if you did this as an experimental measurement, for example, and plotted log of x versus t, what you notice is you don't get a clean straight line that you would expect for a single exponential. What you tend to get is a curve that transitions between a linear region at small t and a linear region at longer t, that indicates the influence of the two exponential solutions that you have in this particular case. Okay, so it's two contributing terms to overdamped oscillations, and the one thing that you'll notice straight up is that the oscillations are quenched, right? So you remember we went yesterday from a system that basically was doing this, so E minus I omega t. And now we've gone to a term that's cleanly exponential. So it's either donk or maybe one kick, and that's it. There is no sort of dying off oscillations that we have in here. The dying off oscillations is what we'll see in the second half when we get to an underdamped oscillator. Okay. All right. So that's our overdamped situation. The next case that we have to deal with is critically damped. So this is situation 2, critically damped. And the reason why we deal with the critically damped situation at all here is that the solution is mathematically not quite the same as overdamped, and slightly interesting in terms of we have to handle it differently because otherwise we miss an important term. Okay, so what we know here is the discriminant we had before is equal to 0, and so what that tells us is that the two roots we get are equal, and they both end up being negative. Okay, so what we've got here basically is Q1 equals Q2 is equal to minus C on 2M. And as you know, C is a positive number, M is a positive number, so this thing must be negative. And for sake of argument, we can call this now minus gamma in the same way that we did above, except we're going to have one single gamma term here. So what we're really saying is essentially gamma 1 equals gamma 2. Okay, so you can imagine this is the limit of the problem above where those two become the same. at first sight, you would suggest, okay, hang on a second, now we should only have one gamma to worry about, and our first guess at a solution would be x of t is equal to a1 e minus gamma t, like so, okay? And so really what we're doing here is basically just taking the case where we have this equation up above and saying, okay, if gamma 2 is gamma 1, then we can add those two exponentials together. What we would have then is something that looks like a1 plus a2 e minus gamma t, and then we might as well call a1 plus a2 just a1 because it's really just a constant, and get that term, okay? Now, the interesting thing is, and this happens quite a lot in physics, it's a logical place to start, right? And so you would start with that term and you would work through, you would come up with some predictions, you would then try to apply them to an experimental system, and you find out, well, actually it gives me the wrong answers, okay? And so then you go, okay, well, my model is not working very well, I have to come up with a new model, I have to add something to it, okay? And so you see this time and again. You see it in the development of special relativity. When velocity becomes very high, Newtonian mechanics doesn't describe situations very well, and so you have to come up with some new maths to get that to work. Quantum mechanics is the same. Here is the same thing, okay? So we take what looks like an easy solution. The easy solution doesn't have sufficient freedom in the mathematics to cover the experimental behaviors, and so you come up with a new situation for this, okay? So what we do to fix this is we actually go back and rewrite our equation of motion and solve it again, rather than just take a guess solution that's inspired by something that we already did for a slightly different scenario, okay? So really what we're doing in some specs is, rather than going critically damped is the same as overdamped because it's a limiting condition, we're going overdamped is here, this is the limiting condition, and the maths has to be handled slightly differently to get the right answers, okay? So we need to go back to our original equation of motion to do this properly. And what we're going to do here is rewrite it knowing that c squared on 4m equals k. And so this is really just taking the discriminant and knowing that because the end is 0, we can go c squared equals 4mk, and then we can just pull the 4m across, okay? So we can write this equation simply because we're in the situation where the discriminant is equal to 0 and not greater than or less than 0. And we know that this thing we can write instead, if we want, as gamma squared m, and this comes about essentially because of our definition of gamma up above, okay? So from this bit up here. And so the two ways to see this is that c is equal to 2m gamma and k is equal to m gamma squared, okay? The second one you can see quite obviously, and the first one is just a very small rearrangement of the situation we've got there, okay? So now what happens to our equation of motion, which was something like this, mx double dot plus cx dot plus kx equals 0, it now becomes mx double dot plus, we can take our c, so this is 2m gamma x dot plus our k here, m gamma squared x equals 0. And then of course we can pull the mass out the front, right? And we can eliminate it entirely actually because we can use the 0 on the other side. So this is x double dot plus 2 gamma x dot plus gamma squared x equals 0, okay? Basically divide both sides by m, and 0 on m is 0. If we have this, what we can do here is we can now factorize this into two pieces, right? And the two pieces look a little bit like this. D on dt plus gamma, d on dt plus gamma times x is equal to 0, okay? And I'll let you check for yourself by working backwards that you go from here back to there, okay? It's just a matter of working through the derivative and then multiplying it out, and you should get exactly that term back again. Now, what we can do is bring this x into one of the two terms in here, okay? So we would write this as d on dt plus gamma, dx on dt plus gamma x. And it doesn't matter which one we do, right? They're interchangeable, so it's really the same thing, either way of writing it. And what we can do here is call this a new variable u. And what we then have is d on dt plus gamma u is equal to 0, where u is just dx on dt plus gamma x. And then this thing down here we can now expand out. So this is du on dt is equal to minus gamma u, okay? So you can spot here for a moment that we've basically got two DEs, right? There's a DE that links u to x, and there's a DE in u. So we've sort of just separated this thing out into a pair of differential equations that we have to handle, right? Okay, so this second equation, this equation here, we can integrate that, right? And we know what the solution for that is. It's going to be u equals a e minus gamma t. And you can check for yourself by taking du on dt that this thing actually works. Okay, so this is just a trial solution for that guy, and it actually works out to be the right solution there. Okay, and so now we can take this piece here and combine it into this piece here to take the next step in this, right? So what we're going to do here is go a e minus gamma t is equal to dx on dt plus gamma x. All right? And so all we've really done is taken our second order DE, factorized it, done a substitution, solved that, and then used that substitution back to get ourselves a new DE here. So really what we're basically doing is taking the original DE that we solved in the first place for the overdamped situation with a really simple solution, and we're just rewriting it for the critically damped case using the fact that we know the discriminant is 0, so that we can recast that equation and solve it via a separate means. Okay, so we're just taking a slight modification here. Okay, so we can basically just deal with A here. So essentially take this E minus gamma T term across to the other side. So this is gamma X plus dx on dt times E gamma T. Okay, and of course when you take it across the other side you change the sign on the exponential. And we know that this thing is basically d on dt x E gamma T. Okay, this one I actually will do really quickly just to convince you this is right. So if we do this derivative in here, we know that x varies as a function of time, right? So we've actually got two terms. We have to do this by product rule. So we would have dx on dt E gamma T plus x d on dt E gamma T. And of course this ends up being dx on dt plus this term over here will get as a gamma, x gamma, E gamma T. Okay, so just proving that that solution actually works just in there. It's perfectly okay, right? So what we have here is A equal to d on dt xe gamma t, and we can integrate both sides again in this particular case, right? Whoops, let's just, come on. Okay. So we're going to take A and integrate we're going to take it and we're going to integrate both sides. Okay, so if we do this, our A will become AT, and of course we have to add a constant here, B, and we care about this constant. Okay, it actually ends up being important in the solution. And then the integral with respect to time of the term on the right just negates the time derivative of the front. So it's going to be X, E, gamma, T up the top here. Okay. All right, so now we can isolate X again. So what we have here is X of T is equal to A T plus B E minus gamma T. And we get our minus back by pushing the exponential over to the other side of the equation. And you'll notice now that this looks very similar to our initial trial solution way back up here. Okay, so up here we had essentially A1 E minus gamma T, and then we decided that this would actually be from this term up here, the sum of two constants. And we sort of have that, right? We have E minus gamma T down here. So we have this exponential bit on the end. We have a sum at the front, but now one of the two constants is actually carrying a T in here, okay? And this is pretty much the crucial part of critically damped oscillator. When that discriminant goes to 0, it allows an additional term to pop into your solution that has a term in T. And so if we actually expand this thing out, what we've got is ATE minus gamma T plus BE minus gamma T. And what's interesting here is that this term on the end looks very much like this term on the end above. But now this term on here compared to this term up here is carrying an extra term in T, right? Perfectly good mathematical solution here, because we can take an experimentally damped oscillator that we set to be critically damped, and creating these systems can be challenging, but you can certainly make them. And you find that you do need this additional term to describe the behavior properly. And so what we end up with is a system that drives itself back to equilibrium very, very quickly in terms of time, and we would basically say optimally. Critical damping is probably the best damping that you can get in terms of quenching oscillations in a system. And it comes about because of this time term that's built into that term out the front. Okay. In both of these cases, if you plot them on a log x-axis versus t, you don't get a straight line, right? There's two exponentials in each of them, and both of those terms contribute. But in this case, as you drive your discriminant from being positive towards 0, you go progressively from an overdamped situation where you damp the system out without any oscillations, but it takes time to decay off, to optimum decay of those oscillations down to 0 amplitude very, very quickly. Okay, and this is why we care so much about critically damped situation, because if you're trying to make a system that damps oscillations, that's where you want to be, because it's the most effective. All right, let's take a short break here, and then we'll come back and deal with underdamped situation.